Right, in this lecture, we're going to look at transport properties of condensed matter systems and ill condensed matter systems. This is an area which is slightly outside thermostatics, but it deals with systems which are very, very close to equilibrium, but where there's some kind of motion. And we're going to spend a lot of time talking about this area because it is an interesting area and has many, many applications. Okay. So the subject of thermodynamics and statistical mechanics developed in the 19th century, which was one of the great areas or times of human progress, particularly in science, but also in moral issues, the abolition of slavery and things like that. And it's a very, very optimistic time. Lots of progress made around the world. And if you look at the history of physics, for instance, there's enormous amounts of progress made in the 19th century. However, this period came to an end when the First World War began, and since then, pessimism has dominated the world. With the odd respite in the 1920s after the First World War, things were getting better. In the 1950s, after the Second World War, things were also optimistic. But generally, the attitude of human beings has been very pessimistic since then. So, we're going to start dealing with the kinetic theory of gases, which most of you have already understood before and which you've seen previously in this course. This is one of the great triumphs of the 19th century science, and it's proper mature physics. Where's my pen? There we go. Okay. We don't have only one particle or two particles, but many, many particles interacting very, very strongly. Now, this kind of subject is part of condensed matter, but even in ill condensed matter, it's like you have in gases, we get very strong interactions. The interactions are very strong, but only over a very brief period, like 1 picosecond is the collision time. So the two molecules collide, 1 picosecond, they go apart, and you don't see them again. Okay. Now, in this kind of subject, we're going to be ignoring details. As the Americans say, don't sweat the small stuff. Okay? And that's true in stat mech in general. We don't worry too much about the details of all the intermolecular forces. Okay? For us, oxygen and nitrogen and uranium hexafluoride, they're pretty much all the same. We treat them all the same. Now, that's because we're physicists. If you're a chemist, of course, they have great pleasure in describing how oxygen and nitrogen are different. But for a physicist, oxygen and nitrogen are basically, for most purposes, just the same thing. Okay. Now, in our system, however, we've got a lot of randomness, and the randomness allows us to make predictions. Okay, and it's because of all this randomness, many particles interacting, that these methods can be applied across a full range of things which are outside of physics: social systems, financial systems, biological systems, etc., etc., etc. So if you ignore the details of interactions, you can often make very, very powerful predictions, and that's what we're going to be doing now. So what's the motivation for this kind of thing, for the transport processes? Well, we want to try and solve problems which are close to equilibrium, but not quite equilibrium. So suppose you have a hot brick and a cold brick, and they're connected by some, an iron rod, for instance. We want to know the dynamics. How does the heat flow from the hot brick to the cold brick? Okay, how long is it going to take? How much heat is flowing per unit time, etc., etc., etc. How long does it take if this brick's at 200 degrees and this one's at 100 degrees? How long does it take for them to reach equilibrium? Okay, and this is the kind of question we're going to try and answer. Similarly, if you have a golf ball or some other sphere moving in a liquid, what resistance does it feel? How fast does it go? Okay, under gravity, for example. Or you can look at the case of perfume, the smell of a perfume coming out of a bottle. How long does it take to disperse in the environment? These are the kind of questions we'd like to answer. Before we actually go and look at the details of this, I would like to tell you about a few books which are very, very interesting and which you might like to look at some stage. Now, I know in most of your courses you're so busy doing assignments and quizzes and things, you have almost no time to do to read. but it's a very important part of your education to go and read other things. The first book is one by a Cambridge physicist called Sir James Jeans. Here he is with his second wife, and I presume their baby. And he wrote a couple of books on kinetic theory of gases, but the first one, the one that's more interesting to us, is called Introduction to Kinetic Theory of Gases. And that's a great book about this subject, which is, it's not obscurely mathematical. It's actually a physics book. It concentrates on the physics rather than on the mathematics. That's a very nice book to go and look at. You can find it on the web very easily. Second book of a similar nature, again by a Cambridge physicist, this time David Tabor, a more modern book, called Gases, Liquids and Solids. This book is also really helpful. It really does focus on the physics of the systems and not on the mathematics, and you get a very good picture of what's going on physically in all these kind of systems. And the third book, which is actually a chemistry book, but a book on physical chemistry by Atkins and DePaula, which I will use, at least for the illustrations in this lecture. This is also a really good book focusing again on the physics of the system. Okay, you can find, of course, many other books which are obscurely mathematical, hundreds of pages of equations, and which most students will not get a lot out of. But these three books, you read them, you will see that they're very nice books to read. You can sit down as a physicist and read them, okay, like you read a novel. Okay, so to start off with, we need to look at flux and current densities. Now, how do we define those? Well, you've actually seen these before. So, for instance, you've seen the charge current density. So, for instance, when you're dealing with electromagnetism. Okay, so this is a phenomenological thing. We're dealing with slightly non-equilibrium systems, just outside the boundaries of equilibrium stat meg. Okay. And in electromagnetism, we use the current density J, i.e. the charge moving through a surface per unit area per unit time. Okay, so you have some charges here, and you have some imaginary surface like that, and you just count the number of charge per unit area, moving per unit area per unit time, and you get a charge density J. Okay, and usually this current density is driven by an electric field caused by a battery, for instance, okay, and you get J equals sigma E, the sigma of the conductivity. So that's the usual thing in electromagnetism. You get that equation. That's what you're used to. You're used to current density, number of coulombs per unit area per unit time. In this particular lecture, we'll be dealing a lot with matter fluxes, okay. So we introduce a matter current density, okay. So the matter current density is the number of particles passing through an area per unit time. Like electric current density, matter current density is a vector, okay? But often we'll ignore the vector nature of this thing, okay? Now, the simplest scenario for this is you have a high concentration region, a low concentration region, and if you do the experiment, what you find is if you have those two regions, there's a matter current density which flows from the high current region, from the high concentration region to the low concentration region, and it's proportional to the gradient of the density, the number density. So number of particles. C is the number. C is the concentration, which is the number of particles per unit volume, and that's what the matter current density is. Okay, phenomenologically, you find that you do the experiment. Now, we now introduce something called Fickian diffusion. Okay, in Fickian diffusion, the matter, which we just looked at, current follows a concentration gradient downhill. So the concentration gradient goes from high density to low density, and the current density is proportional to the negative of the concentration gradient, which we've just seen. Okay. So, how do we get a matter current density when we don't have any external field? Well, often we won't have an external field, but it doesn't matter. Okay, remember when we went to, we go back a little bit, when we deal with charge current density, we normally have an electric field, and the charge current density is proportional to the field. Okay, so that's what you're used to. But here, in this case, for matter current density, we don't have a field. or we have is a high concentration of particles or a low concentration of particles, and we still get a matter current density. So how does that work? Well, what happens is that you have these particles here, which are randomly moving about all over the place, and these particles here, which are randomly moving all over the place. And they're only doing random walks. But of course, if you put a barrier down the middle here, and you look at the number of particles crossing that barrier, because there are more particles on the left-hand side than the right-hand side, you will get effectively a net current from left to right. Okay, so that's the reason why you get this kind of current density, matter current density, I mean. Okay, another way of looking at it is to look at the chemical potential. If you write down the formula for the chemical potential, we'll find the chemical potential here, mu is equal to some constant plus universal gas constant times the temperature times the log of the concentration. And remember, if you have a system, the chemical potentials of the same species try and equalize all over the system. So this means that if you have any gradients in the concentration here, you will immediately have a driving force that will give you a current. So another way of thinking about this is in terms of chemical potentials. The chemical potentials must be equal, so the driving force to equalize the concentration. Right, now, I've told you that the matter current density is proportional to the negative of the concentration. I haven't told you what the proportionality constant is, and that turns out to be something called the diffusion constant, which is normally given the symbol big D. It has units of meters squared per second and SI units, and D can itself depend on all kinds of factors, including the concentration, but often we'll ignore the concentration dependence on D. So sometimes you'll find D is a function of C. We'll normally ignore that. But in most cases, you will find the diffusion constant is proportional to the temperature, and that's often quite important. Okay, so that tells you how rapidly things diffuse. Okay, for given equal amounts of concentration gradient. That's the diffusion constant. So that's matter flux. So we've had electric charge flux, which you're familiar with. We've now had matter flux, which you might not be so familiar with, and there's heat flux. Okay. So the heat flux, which is a thermal flux, you can get that from the current density of energy due to thermal gradients. So here we've got a thermal gradient. Suppose we have a thermal gradient to TDX. And you want to say, well, what sort of thermal flux will we get? So we have a hot body here, a cold body here, and we will get some thermal energy flowing that way. Okay. Again, it flows from high concentration, if you like, hot to cold. So that's the way it flows. So there's a negative sign here. It's proportional, at least if the temperature gradient is not crazy. It's proportional to the gradient of temperature. And the thermal energy flux is the energy unit time unit area. It's the power unit area, if you like. So that's what the heat flux is. Okay. So that law tells you something which is bloody obvious, which is that heat flows from hot to cold in proportional to the temperature gradient. The second bit is not so obvious, but it's true. Okay. This thermal flux is called a whole lot of things: heat flux, thermal flux, heat flux density, and K here is called the thermal conductivity. It has units of watts per Kelvin per meter. Okay, if you figure it out. Okay, that's what. Just like we had a diffusion constant before, we've had a diffusion constant, we've had a conductivity. Now we've got a kappa, which is the thermal conductivity. So you see there's a pattern arising here. All these systems, for instance, they're linear. They're very, very linear. The thermal flux is proportional to the gradient of the temperature. Okay, the matter current flux is proportional to the gradient of the concentration. The electric current density is proportional to the gradient of the voltage. Okay, so the third or fourth thing we need to deal with is momentum flux. So to deal with that, we need to introduce go back to viscosity. Well, I've already mentioned viscosity at one stage before, but let me reintroduce it. And the way we introduced it before was in Stokes' law. So Stokes' law gives us the drag force on a sphere as it travels through a fluid. So a sphere, you might be dropping it under gravity, so it's starting to fall. There's always a drag force if you're dropping it in honey or oil or water, whatever. Okay, and if the sphere is not moving too fast, then what you find is that the drag force you feel, which was first calculated by Stokes in probably the mid-19th century, is given by 6 times pi, some very boring constants, times the radius of your sphere, times something called the viscosity, times the speed. Okay, and that's was first calculated by Stokes, but it's been experimentally verified millions of times. Okay, used of course famously in Millikan's ore drop experiment. Okay, and this constant here, the viscosity, is a phenomenological constant which you can calculate in some cases. If you will calculate effectively for gases, but for other systems it's more complicated, and it varies incredibly across from different materials. It's nowhere like all the same for all the materials. So in air, for instance, air is not very viscous. It's 10 to the minus 5 Pascal seconds. That's our units there, Pascal seconds, SI units. Water, for example, is 100 times more viscous than air. Okay, and that is why, for example, ships don't travel very fast. Okay, because they're forced to deal with the drag of water. And if you have a ship, what you do is you try and make as much of the ship above the waterline as possible, even though that causes some instability. So we can go to, for instance, olive oil, which has viscosity which is, again, 100 times more than water. And glycerin, which, depending on what the temperature is, again, 10 times more than olive oil. Polymer melts, plastics, if you melt some plastic, it has even higher viscosity. Pitch, even higher still. And at the moment I'm doing some glass courses at ANU, and glass has an incredibly high viscosity, but it does flow, and that's very, very temperature dependent. If you take it out of the furnace, for instance, it flows very, very well, and then you put it in the air and it starts to cool down. Then you have to put it back in what's called a glory hole to heat it up again. But this is, glass is still extremely viscous. You couldn't do glass blowing if glass had the same viscosity as water, for instance. It wouldn't work. Okay. So, let's talk about momentum flux and viscosity. Okay. Consider a fluid, or a liquid or gas, they're both fluids, flowing next to and parallel to a flat wall in the x direction. So here's my x direction. The fluid is flowing this way. Okay. But there's a wall here. Okay. And using the standard bounding conditions at the wall, the fluid would have 0 velocity. But as we go further out, its velocity keeps getting bigger and bigger and bigger and bigger and bigger. Okay, so it accelerates out there. Okay, so if we do that, we can look at the fluid by dividing it into completely imaginary layers. So there's going to be these layers here, which are totally imaginary. Okay. But the fluid in this layer is moving faster than the fluid in that layer, and that layer is moving faster than the fluid in that layer. Okay? Layers further away from the wall have larger x speeds, and therefore larger momentum per unit volume, if you like. The layers accelerate and retard one another because their neighbours move at different speeds. Okay, so this one's moving fast and will be retarded by this one. Okay, and accelerated by that one. Okay, so what we're going to do now is introduce a momentum flux. This is a bit weird, this thing. It's much weirder than the diffusion constant, the matter flux, for instance, or the heat thermal flux, because it's usually a tensor, and because if you look at the formula written down here, the momentum flux of x momentum, which is the amount of x momentum per unit area per unit time transported across a plane parallel to x. In other words, it's the amount of x momentum transported across that plane there. Okay, E is the viscosity, and what you find phenomenologically, which is what basically Newton found, is that the momentum flux in the x direction depends on the viscosity. It's got a negative sign there, but it also depends upon the gradient of the x velocity in the z direction. So z here is normal, that's x, so Vx is pointing up there, and the gradient, the momentum flux density is proportional to dvx dz, okay? And so that's a bit weird, and it's generally a tensor, but we won't normally describe any tensor properties. But you can see it's likely to be a tensor here because we've got something in x and a variation in z. Okay, so that's the momentum flux. So let's talk about kinetic theory. So what we've done here is introduce a whole lot of different kinds of fluxes and the constants associated with those fluxes. So we've got sigma, we've got d, we've got kappa, we've got eta. Okay, again, everything's nice and linear. Okay, so we've got all these kind of different fluxes. The first one you're familiar with, and the other three maybe less so. Okay, so let's try and calculate some of these. So what we're going to do is we're going to try and calculate some of these, and even that one, I think, ultimately, on the basis of microscopic statistical models. That's our aim here. Okay, so we're going to do that by kinetic theory, and kinetic theory was developed in the 19th century by people like James Clerk Maxwell, and it's, as I said before, it's one of the triumphs of 19th century physics. It takes predictions from the microscopic atomic world and allows you to make predictions based on that of macroscopic quantities. You know, the thermal conductivity is a macroscopic quantity you can measure. The viscosity you can measure. It's macroscopic. It has macroscopic influences. Okay, I mean you can calculate how long it's going to take to drop a sphere for a sphere to fall in the air. Okay, so of course in kinetic theory you imagine a gas of hard spheres. We're going to go beyond the very primitive model with the hard spheres of point particles to ones where you've got particles of diameter d. So d is the diameter. Okay, and the way to think about this when we're trying to calculate the collision frequency, so the first thing we want to do is calculate this collision frequency, which is the number of collisions per unit time. Okay, so what we do is we take a one sphere moving in the system and concentrate on that, and we freeze all the other spheres. We imagine them frozen. Okay, and it will this sphere we've isolated is going to move through the gas, okay, at a speed v rel, which is speed relative to all the other molecules, and we're going to look at how it moves in a time delta t. Okay, now when it does that, it sweeps out a collision tube of area sigma is pi delta t, pi d squared. Now, why is it pi d squared? Because pi r squared is that area. The area of the sphere would be pi r squared. But you've got to realize that it's surrounded by other spheres of diameter d, and so effectively we want to know how many collisions it's going to have. So we have to actually double its diameter and look at that area. Okay, any sphere which has its center within that area is going to be hit. Okay, provided it's within this tube as well. Okay, so for instance, this one in the time delta t will be missed, no hit. Okay, whereas this one here, where are we? This guy will be hit. He's got he's in the way. He's within that big sphere of big cylinder of length, which is v rel delta t. That's its length. That's how far this thing will move. And sigma is the air cross-sectional area. So the volume of this particular cylinder is this thing here. Okay. The number of molecules in this tube, which we just calculate the volume of, let me erase all that kind of stuff. The number of molecules is just the number density, which we know about, times the volume of the tube. So the number of molecules which are going to be hit is just that in the time delta t. And the number of collisions per unit time is just that divided by delta t. So that's the answer for the number of collisions per per unit time. So you can go away and think about that, but that's the answer. It's just common sense. This is just accounting. Most of physics is just accounting, and this is what we're doing here. Okay, so next one. So let's actually look at some numbers here. And the numbers we have are for nitrogen. And we're going to look at nitrogen at 1 atmosphere and 25 degrees C. If you put in the numbers for kinetic theory for that, you get the RMS speed of your molecule to be about 515 meters per second, roughly the speed of sound, a bit faster. And the relative velocity, which is a somewhat hazy concept, which we're not going to gloss over, fudge through this. It's actually root 2 times the RMS speed. You can figure out why that might be the case. So we're going to do that, and that turns out to be 728 meters a second. The cross-sectional area of the molecule, the cross-section for nitrogen is 0.43 nanometers squared, which you can measure via various methods. Actually, measuring the viscosity is one of those. And the number of molecules per cubic meter we can just get from the ideal gas law, and it's big, 2.4 times 725. If you plug all those numbers in, we get a rate of collisions which is incredibly high, 10 to the 10 collisions per second for a single nitrogen molecule. Okay, that's a lot. Okay, so on the microscale, nature is very, very violent. If you go down to this scale, you are constantly being hit. Okay, now the interesting thing is you are constantly being hit despite the fact that the volume taken up by all the molecules is what you can figure that out fairly easily. I won't go through it in detail here, but you can figure out that the actual fraction of the gas, which is actually molecules and not just empty space, is only that. It's 0.00065. Okay, so the molecules are moving very fast and making many collisions, despite the fact that most of space is empty of molecules. And this is very, very useful in chemical reactions, because in chemical reactions, sometimes you want to do chemical reactions in gas, and this helps you tremendously. The gases are very dilute, but you're getting collisions all the time, and so things can interact. Okay, so what we need to introduce now is the idea of the mean free path, which is normally given the symbol lambda. It's the distance moved by a molecule between collisions. So it's distance moved between collisions. Okay, that's lambda. Okay. The time between collisions is 1 on z, and this relative speed is vrel, so it's very easy to figure out what lambda is. It's just vrel divided by z, which turns out to be kT, temperature, divided by the cross-section area, divided by P, the pressure. Okay, you can get that from the ideal gas law. And if we do that for nitrogen, we find it has a mean free path with the previous parameters at 1 atmosphere and 25 degrees C of 95 nanometers, okay, which is about 10 to the 3 molecular diameters. So it's moving about 1,000 molecular diameters before it collides with another nitrogen molecule. That's a typical mean free path for nitrogen. So it's good to keep these kind of numbers in your head. Most of the space is empty, but the number of collisions is very, very large, and the mean free path is many, many molecular diameters. So we need to introduce two kinds of regime here, because in an experiment or a real physical system, you will have two length scales. You will have the mean free path, which is what we introduced, and you'll have something which is even more basic, which is the external length scale, which might be the size of your box, the size of your room, the distance between two plates. If you have two plates, this will be your length scale, which is probably relevant. Okay, and there are two kinds of regimes here. There's the collisionless regime, where the mean free path is much larger than your box size. So basically, what happens is, if I only have a couple of molecules here, these molecules will undergo a walk like this, and they will traverse the box many times before they undergo a collision. Okay, so that's typical if you have a very, very rarefied gas. Okay, if we have a system which is, for example, in the opposite regime, where you have a mean free path which is very small compared to the length of your box, size of your box. That's, for instance, true of the gas molecules in a room. The gas molecules in a room, as we said before, let's have a look at nitrogen. They undergo a collision in 95 nanometers, roughly. And of course, most rooms are much larger than 95 nanometers. So if you're nitrogen in the room, you collide crazily with all the other nitrogen molecules before you reach the side of your box. Okay, that's called the hydrodynamic regime. That's the regime where things are all evened out. You get many collisions, and you get things equilibrated quite fast. The collisionless regime, much less so. So, having introduced that, let us discuss effusion, which is basically molecules flowing through a hole, and the collision flux. So, let's introduce that. So, the collision flux, which will give the symbol big I. I is the number of collisions per unit area, per unit time, against some area in the gas. Now, that area could be real, it could be a wall, it could be a hole, or it could be completely imaginary. Just imagine slicing your gas into two regions. Just imagine what the collision flux is. So, let's make this the x direction. Okay, we have a couple of molecules here, there and there. Okay, and we're going to take an area A perpendicular to the x-axis. So this is the area A just here. I suppose here's my area A just there. Okay, and I'm going to look at molecules colliding with this. Okay, now we're going to look at molecules which have which collide with this, and the molecules which collided with it in a time delta t. So we're going to let them collide within a very small time delta t. Now, if their velocities are low, or they're located within close to the wall. Sorry, I should say that again. If a molecule has Vx bigger than 0, it will strike the wall in a time delta t. If it lies within Vx delta t, this would be a delta there, delta t of the wall. So you have to lie within that distance of the wall to strike the wall. Okay, this one out here is far too far away for that given velocity, and it won't hit the wall. So this one won't hit the wall, it's just too far away in a time delta t. This one, it's within the box of Vx delta t, and it will hit the wall. Okay, that's just common sense. Okay, assuming there are no collisions with other molecules. Okay, which is what we're assuming. We are assuming we're in the collisionless regime because we take delta t to be small. Okay, so all molecules in the volume Vx delta t with Vx greater than 0 will collide with the wall. So I just multiply by the area to get the volume. So this gives me the volume of this thing here. In that volume, all the molecules which have which are in that volume will collide with the wall. Okay, if Vx is big enough. Okay, now if n is the density of the molecules, the number density, the number of collisions is given by this. Okay, you integrate over all the possible velocities Vx. Okay, you multiply by the density times a delta t. So this gives you the volume we have here, and then you can go and put this distribution function in from kinetic theory, and you will get the following result. I'm not going to do the integral for you, but you can do that integral fairly simply. And then the collisional flux is just that divided by the area. So it's the number of molecules per unit area, per unit time colliding with the wall, and that collisional flux is given by that, which you can write in terms of the pressure and the temperature and the mass of your particles. Okay, assuming you only have one species. Okay, now how does that vary with all the kinds of parameters you might like to look at? Well, it increases with the pressure. Okay, and it also increases with the temperature, because in a container with fixed volume, the pressure is proportional to temperature. So it looks like it's going to go down as a function of temperature. But if I took a system which had, shall we say, a fixed volume, I increase the temperature, I know the pressure is proportional to temperature, so the collisional flux will still increase with temperature, even though it looks like it's going to go as 1 on the square root of the temperature. Okay. So we can write this collision flux as being equal to a quarter of the number density times the mean velocity, okay, the mean speed. Okay, because the mean speed is 8 kT on pi and the square root of. So that's the usual way it's written, a quarter number density times the mean speed. Okay. So where is this useful? Okay. Well, it's useful in looking at effusion. So effusion is the process by which gas escapes from a small hole in a container. And Thomas Graham, who I suspect was Scottish, was the first to investigate this thoroughly. Not the first to investigate it. Often things are named after people who investigate it the third time or the fourth time. So Graham's law states that the rate of effusion is proportional to 1 on the square root of m. And you can see if we go back here that the collision flux is proportional to 1 on the square root of m. There we go. So that's where Graham's law comes from. We'll look at this in more detail. So this is useful, I put useful in inverted commas, in isotope separation. So if you look at uranium, for instance, the uranium get out of the ground has at least 2 isotopes. There's U-235 and U-238. Now U-235 is a fissile material. In other words, it will produce lots of neutrons when it's hit by other neutrons. U-238 is not. Okay, but in nature, U-238 is 130 times more abundant, 139 times more abundant. Okay, so we'd like to get our hands on U-235, despite the fact it only makes up a very small fraction of the isotope of the naturally occurring uranium. Okay, and we can use effusion to do this, and this is what they did in the Manhattan Project in the Second World War. They're trying to make a nuclear bomb before the Nazis do. So what they did was they used this m to the minus a half dependence to make the first atomic bomb. So you have here, you've got basically the way it works is very simple. You've got a feed of gas. It's uranium hexafluoride gas coming through here, and you've got little holes in the side of the tube here, and in those through the little holes outflows the isotope you want, slightly enriched because it goes as m to the minus a half. Okay. So, to do that, they needed to build an enormous isotope separation building in Tennessee in 1944. It was the world's largest building until it was demolished in 2013. It's 1 mile long, 4 stories high, 152,000 square meters of floor space, which is 10 times the St. Peter's in Rome. Now, the Tesla Gigafactory is even bigger than that. It has that much floor space and that much volume. But this is an absolutely enormous building. Sort of thing when you go to war, you do. Okay, so let's look at isotope separation. Let's look at the two isotopes, 238 and 235. If you look at the rate of effusion through a small hole, you will find this is the rate you get for those 2 isotopes. One of them diffuses at a rate which is 1.00636. It diffuses at a slightly higher rate than the other one. Okay. But in fact, things are actually worse than that because this gas, the gas we use, is not uranium. You can't make gaseous uranium, at least at reasonable temperatures. What you do is you make uranium hexafluoride. You mix it with fluorine, and you get this so-called hex. And that makes the system a little bit worse because now we have things perturbed by the hex, and the actual effusion rates only differ by 0.4%. Okay, so that's how they originally made atomic weapons. Okay, now in practice today, we use centrifugation, which is a different method, which I think we will study in a tute somewhere, and it uses 60 times less energy than fusion, so it's much more efficient. And Iran, for instance, has 20,000 centrifuges, which they would claim are being used to separate isotopes for peaceful purposes, okay, and not to be used to make bombs to drop on Israel and Saudi Arabia. But whether you believe that or not is open to you. Okay, now let's do an example of effusion, the rocket effect. Now here we have Mr. Squiggle, who was on television when I was very, very young, and he came down from the moon every so often and drew pictures with a pencil attached to his nose. There, he had a nose instead of a pencil, I suppose. Now, a gas cylinder has a small leak through a hole of area A. Okay, the gas leaking out produces a force on the cylinder. How big is this force? Okay, well, the force is the rate of change in momentum, and the rate of momentum loss very, very, very roughly, this is a very rough calculation, we're leaving out numerical prefactors here, which can be important, is equal to the area of the hole times the times I, okay, times the momentum, which is roughly the mass times the mean velocity, okay. And if you write all those out, you'll get this, and then you collect the terms in v mean squared, and because we know how v mean squared depends upon the temperature, etc., we can write it like that, which is A times P, and that's exactly what we expect. The rate of momentum loss is proportional to the area times the pressure. Now, this is, in fact, the answer here is a little bit different, but in reality, because we've looked at numerical proof factors. But that's just to check on our result is somehow sensible. Okay. Now, let's try and calculate the diffusion constant. Okay. Now, we're going to do an estimate of this first, and then we're going to correct our estimate. So, the first thing we do is take an area A perpendicular to the z-axis. So here's our z-axis here. Okay. And we're going to let, at their area A, that's their area A, we're going to let z equals 0 just here. Okay, just there. Okay. The molecules crossing this area have travelled a distance of one mean free path, roughly, since their last collision. So they've got molecules zipping across here and zipping across here, and some of them are going away, of course, some of them are zipping elsewhere. But the molecules actually cross that surface have travelled roughly a mean free path, lambda, since their last collision. They can be going from left to right or right to left. It doesn't really matter. Okay. So, the densities on either side of the area are, we can calculate those, or estimate them by Taylor series expansion. So, so let's take our two plates, which here's our area here, and we're going to take a plate at minus lambda and a plate at plus lambda. Okay, and the density of the molecules at plus or minus lambda at these two plates is equal to the density in the middle plus or minus lambda times dn dz. That's just Taylor series expansion. Okay, and we're going to take the n dz, the density respect to z at z equals 0. Okay, the current density of particles moving from left to right, so going from left to right, is given by this. That's J left to right is given by I at z equals minus lambda, in other words, here, which is a quarter of n at minus lambda, that's z equals minus lambda, times v mean. Okay, and the current density of particles from right to left is similarly given by the same sort of thing, but it's z equals lambda, so you get that expression there. Okay, so the net current density is just the ones moving from left to right minus the ones moving from right to left, which gives us this particular answer here, which I'm sure I've left off a constant, which should have a lambda here. So there should be a lambda in there. If you sum up the two terms, I've just dropped off the lambda. And that you can write, remember we introduced this diffusion constant before, which is minus d dn dz. That's our definition of diffusion constant. Okay, so from that you can read off the diffusion constant. It's a half times the mean free path times the mean speed. Okay, that's our diffusion constant. Right, now this diffusion constant is unfortunately an approximation because I've completely fudged things here. I made all kinds of weird approximations. Okay, in particular, the molecules are not moving at right angles to the surface. So these molecules here, where do we go? Let's go back here. The molecules which are here, for example, they're not necessarily going like that. Some of them are doing this. They're still moving towards the surface, but they're moving at some, angle which is almost parallel to the surface. Okay? Now, ones that do that, of course, well, they have the chance of actually colliding with another molecule. A significant chance. Okay? Of course, everything's stochastic here. And they may take a long time to get there. So these ones going zip, they're fine, maybe fine. Even these ones, of course, they can still collide with another molecule because the mean free path is statistical measurement. It's not guaranteed you won't be colliding in a length lambda, but these ones have a much higher chance, okay? So if we take that into account, which is a much more complicated calculation, we get a factor of 2/3, and we need to introduce that, and we get a diffusion constant, which is 1/3 the length of the mean free path times the mean speed, and that's a calculation of the diffusion constant. Okay. Now, the diffusion constant D. All right. For molecules of diameter d, we can estimate this now. The collision cross-section, an area, is just that, which we met before, and the mean free path is just kBt on sigma p. Okay, so this means the diffusion constant, which is lambda v mean, decreases with increasing pressure. Okay, the molecules move more slowly, so they diffuse more slowly. If you increase the pressure, the molecules diffuse much more slowly here. Okay, because lambda goes as 1 on p. Okay. Also, the smaller molecules diffuse faster because d is smaller, and this thing is also smaller. So lambda goes up in those cases, and d also goes up. So lambda goes up and d goes up. Okay. Since v is proportional to the v mean is proportional to t to the half, hot molecules diffuse more rapidly. So this gives us a diffusion constant which more or less obeys common sense. Okay. And does this just repeat the previous slide? So we don't need to show that again. Okay, and that's also repeated that slide. So, and that's the end of this particular lecture.